Hey gang, welcome back for a second delicious taste of the rainbow. We ended last time talking about trichromatic theory and the fact that the visual system uses three different types of photoreceptors, three different types of cones, in order to code for different wavelengths of light. So using the combined responses from those three different cone types, we can figure out the quality of light that's actually present. So we know that something is blue and not yellow because short wavelength blue light causes a large change in the activity in those short wavelength sensitive cones and small changes in the long wavelength sensitive cones. So our next step is describing what the retinal ganglion cells do with the input from the cone layer. So the reading introduced you to this, but we'll do a bit more unpacking of this content here. So as you read, the retinal ganglion cells are arranged in opponent pairs that get input from multiple cone types. There are bipolar cells involved here too, but we're going to kind of gloss over those and just talk about how the signal is combined as it goes from the cone layer to the retinal ganglion cell layer. And retinal ganglion cells are arranged in what are called opponent pairs. So here's an example of a retinal ganglion cell that is a green-red opponent pair in which the medium wavelength sensitive cones have an excitatory relationship with the retinal ganglion cells and the long wavelength sensitive cones have an inhibitory relationship with it. So what that means is that in the presence of medium wavelength or green light, this retinal ganglion cell is going to increase its firing rate. So when this retinal ganglion cell is showing an increased firing rate, that indicates the presence of medium wavelength green light. In contrast, when there is a change in activity in the long wavelength sensitive cones, that has an inhibitory relationship with the retinal ganglion cell. So a firing rate that goes below baseline for this particular retinal ganglion cell signals the presence of long wavelength or red light. So we can code for red and green using the same neuron. We talked earlier about the benefits of having a baseline firing rate, and this is another clear example. So firing rate above baseline signals one thing, and a firing rate below baseline signals another thing. This is a lot like what we talked about in the vestibular system, where the hair cells in the right ampulla are excited by turning to the right, and hair cells in the left ampulla are inhibited by turning to the right. So we also have opponent pairs for the blue-yellow pair. So for this retinal ganglion cell is blue positive and yellow negative, meaning that short wavelength sensitive cones have an excitatory relationship with this retinal ganglion cell, and medium and long wavelength sensitive cones have an inhibitory relationship. So when this retinal ganglion cell is firing fast, it signals blue, and when it's firing below baseline, it means yellow. Now note that there are also R plus G minus and Y plus B minus retinal ganglion cells. We're just talking about this type for simplicity. Sometimes people ask why the short wavelength sensitive cones aren't part of the red-green opponent pair circuit. And the reason for that is that short wavelength sensitive cones are not active when viewing green or red light. So the response from those cones isn't important for distinguishing between red and green. Now, it's important to point out that when we talk about trichromatic theory and opponent process theory, these are not like competing theories. They're just different parts of the same process. So trichromatic theory describes the process that is happening in the cones, where we're getting input from three different cone types, and opponent process theory is what's happening in the retinal ganglion cells, where we're taking that information from three types of cones and combining it into two different classes of retinal ganglion cells. So the fact that these cells are arranged in opponent pairs leads to some very delightful phenomena. Let's take a look. I want you to stare at the little plus sign just above the horizon and don't move your head and don't wiggle and don't blink and just keep your eyes fixed on that plus sign. Keep staring. Keep staring. Just a little longer. This is a black and white image. Isn't that fun? Okay, let's do it again, but this time with a Carleton themed one, not just a Minnesota themed one. Okay, again, stare at the little plus line. Stare, stare, stare. Stare, 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 stare. Keep looking. Keep looking. Again, a black and white picture. What's happening? All right. So the explanation for these amazing color afterimages is a combination of opponent process theory and also some features about how photoreceptors adapt over time. Prolonged exposure to one color leads to perception of the opponent color. Here's why. Typically, in the absence of adaptation, this is the pattern of changed activity that you see in the cones. So when we have short wavelength blue light, we see a big change in the response of the short wavelength sensitive cones, for instance. I want to emphasize here that all of the cones are showing a big change in activity in response to white light because it contains all wavelengths of light simultaneously. So if, for example, we are staring at something blue, after that continuous presence of short wavelength light, the response from the short wavelength sensitive cones reduces. And it reduces because the short wavelength sensitive photopigment is isomerizing or bleaching faster than it can be replenished. The short wavelength sensitive cones are using up their stash of photopigment. Then, when we switch to being presented with white light, the response of the short wavelength sensitive cones changes less than it typically would. The medium and the long wavelength sensitive cones still show a big change in activity because there are medium and long wavelengths present. But even though there are also short wavelengths present when we look at white light, the response of the short wavelength sensitive cones is reduced. It's fatigued. It's lower than it should typically be. So what does that white response look like? It looks like yellow. So, staring at blue and then switching to white leads to the same pattern of neural code as staring at an unsaturated yellow. So that's what we perceive. The things that we've talked about so far about how we perceive color have been limited to the bottom-up input, so what information is coming in. But of course, we know that perception is an inference and we go beyond the bottom-up information. So how do the expectations that we have and the experiences that we bring with us, how do those affect our perception of color? Now, throughout our lives, we've been exposed to lots of different combinations of wavelengths of light. In the bright afternoon sun, there's more short wavelength or blue light than there is in artificial light. At sunset, the wavelengths of light are very different than they are at midday. And yet, if we want to be able to know the true color of something, regardless of the ambient lighting, we need some way of correcting for what the ambient lighting is. Enter color constancy. So one of the real challenges that we face in color perception is that things appear to change color significantly depending on the nature of the illumination. So these red raspberries look really different depending on whether they are out in sunlight or they're under artificial yellowish greenish light. But in both cases, our perceptual experience of them is still that they're red, right? Like, you can tell that those raspberries are red. You see that there's some kind of like filter on them, but you know that in the real world, in the true state of things is that those raspberries are actually red. So this phenomenon is referred to as color constancy, the ability for us to intuit or guess the true color of something despite changes in illumination. So color constancy helps to ensure that the perceived color of objects remains relatively constant even under varying illuminations. And there's some debate about how this occurs. It seems to be some kind of overall assessment about the statistics of the scene that enable us to discount the features that are constant. So what is the benefit of this? Well, if we couldn't do this, we'd be in this constant state of confusion when we go from outside sunlight to fluorescent light. We'd be like, weird, these raspberries used to be red, but they suddenly turned brown. Right? So being able to intuit the true color of something despite changes in the wavelengths present is clearly a beneficial ability. So in the raspberry example, we have different wavelengths of light that are actually reaching the eye. If we use the eyedropper tool and pull out specific pixels, you can see that the actual wavelengths that are reaching your eye are quite different. But our perception is that the true underlying color is the same. Here's another great example. What color does this square appear to be? Probably you're saying blue. How about this one? What color does this appear to be? Yellow? Yes? Guess what? They're actually the same. Let's do that again. Really? Really? That looks really blue. That looks really yellow. But they're actually both gray. Okay, now if you could take away the yellow filter, take away the blue filter, you would be right that there is a photo of a Rubik's Cube and that the square on the left is in fact blue. So you are right about the true color underneath, but you are wrong about the wavelengths of light that are actually present, in that you are not actually seeing them as being gray. So in this demonstration, the same wavelengths of light are hitting your eye. So in both cases, your eyeballs are getting information that is consistent with gray. But depending on the illumination that you assume, you interpret the true underlying color differently. So remember the quote from last time, in which the argument is that what we see as white is the potential to be white, is what would look white under pure sunlight. In the Rubik's Cube example, what you're seeing in that square is its potential to be blue. Because right now it's gray. So we can't say you're just seeing the wavelengths that are present, because you are in fact intuiting something about the true nature of this and its potential to be a color under different ambient lighting circumstances. So in fact, trying to assume true underlying colors despite changes in illumination is the process that is responsible for the wonderful phenomenon, the worldwide sensation that is the dress. If you happen to miss this, the debate is about what color the dress in the image that you're seeing is. Some people say it's white and gold, other people say it's blue and black, some people can switch their perception and see either. One of the most fun coincidences of my whole life is that the dress happened, like news of it broke, not just while I was teaching sensation and perception, but the night before I was scheduled to teach this very lecture in sensation and perception. So I was sitting at home, I was watching a movie, I had already prepped my lecture for the next day, and all of a sudden my phone started blowing up with people saying, "What is happening with this dress thing?" And I said, well, clearly I have to turn off the movie because I need to rewrite my lecture because obviously this is what we're talking about tomorrow. And now we get to keep talking about it every year. All right, so there are two questions that perceptual psychologists are particularly interested in when we talk about the dress. The first one is, why can the same stimulus be interpreted in multiple different ways? And the second one is, why do different people see it differently? Again, like the Yanny Laurel thing, notice that the question of, yeah, but who is right, is not one of the things that we're going to tackle. Perception is an inference. What we're interested in is the inferences that you are making. All right, so to answer question one, we go back to color constancy. The fact is that the dress is, in point of fact, reflecting some short wavelength light. There is a thing about it that is bluish. Now, if we were to attribute the presence of those short wavelengths to the illumination, if you assume it is in blue light, then the blue that you see isn't about the dress, it's about the light. So you perceive it as being white, like in the left panel of the picture here. If you assume that the dress is under white light, then that slight bluish tinge that you see must be coming from the dress itself. So if you assume blue tinted light, you're making a correction for what is under the blue light, and the dress appears white. If you assume whiter light, then the dress looks blue. In fact, yes, yeah, they're the same. Here's another really nice demonstration of the same phenomenon, just to show how much the nature of the illumination affects our perception. Right? Isn't that something? Okay, so it's possible to perceive the same stimulus in multiple ways, depending on the nature of the light that you're assuming. The dress is bluish. If you assume bluish light, then the dress appears to be white. If you assume whiter light, the blue must be coming from the dress itself. But the second question is, why on earth would different people assume different things about the nature of the illumination? Right? In the Rubik's Cube example I showed you, in the part that's under blue light, everybody assumes it's under blue light. In the part that's under yellow light, everybody assumes it's under yellow light. So what's different about this? Why do people differ in the assumptions that they're making? So after the dress happened, there have been a few research teams that have tried to test this question scientifically. The largest scale study to date on this involved over 13,000 participants. They ran it in two phases, an original and a replication of the same study. So the researchers found that white and gold was the most commonly perceived pattern, but nearly a third of people saw blue or black or some other combination of colors. They also asked about lots of demographic and other kind of individual difference variables, age, gender, and so forth. One particularly interesting set of questions had to do with people's circadian rhythms. Some people tend to wake up early and they feel like they do their best work in the morning and they like to go to sleep early. We call those morning people larks. We can contrast them with night owls who tend to like to sleep in and stay up later and feel best at night. The researchers found, strikingly, that the proportion of people who saw the dress as white and gold differed depending on circadian rhythm type. So the proportions of people who saw the dress as white and gold is shown here on the y-axis, and what you see is as we go from the strong night people to the strong morning people, there's a really marked change. The larks, or the morning people, are significantly more likely to see the dress as white and gold. So why on earth would your typical sleep schedule affect how you perceive color? Well, morning people, larks and night owls differ from one another in a lot of ways, and one has to do with the nature of the light that they're most commonly exposed to. So larks see more natural daylight than owls do. And daylight has more short wavelengths in it than artificial light does. So larks' life experience has more bluish light in it than owls. When presented with ambiguous stimuli, perhaps they are interpreting that ambiguous stimulus in the context of their prior experience. So if they assume blue-tinted light, then the bluish tinge of the dress isn't about the dress, it's about the light. So look again. Is it in natural light or is it in artificial light? Yeah, people differ really markedly in this as well. So when this first happened, a lot of people said, yeah, but what color is the dress actually? And actually, the dress doesn't matter. The dress isn't what's special here. I mean, it's a cute dress, but the dress isn't what makes the effect work. What makes the effect work is that it's a low-quality image, and the lighting is ambiguous. It's not clear whether it's in natural light or artificial light. But the assumptions that people are making about the nature of that light is one of the things that influences how they perceive it. So here's data showing how the nature of the assumed illumination affects perception of the dress. And what you can see is that people who assume that it is natural light are far more likely to interpret the dress as being white or gold. All right, so now we can look at how this relates to the circadian rhythm. The researchers also found evidence that owls, night people, are more likely than larks to assume artificial light. So these findings appear to be explained in part by the fact that owls are assuming different kinds of light than larks. Owls are assuming that the lighting is what they're the most used to, that is, that it is yellowish light, and larks are assuming more bluish light. And so their perceptions about the color of the dress are driven by their assumptions about illumination. So the claim is that morning people see a low-quality image and assume this. Night people assume this. Now, it's important to note that the lark-owl characterization doesn't wholly account for individual differences. So even though there were significant differences between owls and larks, they didn't completely explain the patterns in how people perceive this image. That may be because the self-report measure of circadian rhythm is actually a somewhat weak proxy for the amount of daylight hours that someone has seen. So some college students, for instance, may think of themselves as larks because they get up earlier than their friends, right? Like you get up at 8 or 9, you're an early riser, right? But any parents of toddlers would think it's hilarious to say that getting up at 8 is waking up early. So this measure may be an imprecise measure of how much bluish daylight people are exposed to. But what is clear is that this demonstration reinforces two of our themes. First, that perception is an inference. We are clearly going beyond the information that's given and using our prior experience to guide our interpretation of sensory input. And secondly, that we each walk in our own perceptual worlds. It is totally possible for two different people to look at the same visual stimulus and have a very different perceptual experience. Now, since the dress, many other similar demonstrations have surfaced as well. Is the shoe gray and turquoise, or is it white and pink? Which nail polish best matches the shoes? Opinions differ. Now, these are bistable illusions, but again, like Yanni Laurel, they're bistable across individuals, meaning that we only know they're illusions when we talk about them with other people. And think about all the times you've looked at a picture and not said, oh yes, I see this as gray shoes with a turquoise stripe, right? And just said, look at these cute shoes. It's entirely possible that our perceptual experiences are differing from one another regularly, but we only find out about it when we try to describe our perceptual experience to someone else. So these are clear examples, but it's likely that this is happening to varying degrees much more often. All right, and at the end of the rainbow, you find a pot of gold or some problem set questions. See you in class.